Hey guys, welcome to Digital Screening channel on YouTube, and as usual I request you to please go ahead and subscribe to this channel and also like the videos that you really happen to like. Okay, now in the last video I talked about generative adversarial networks, right? Putting together a GAN in keras for cifar10 dataset, meaning we are going to train it on cifar10 dataset. Now you need to change these networks a little bit if you are going to use different datasets, and that little bit is basically defining what the input image size is going to be for your discriminator, and also what the output size is going to be for your generator, because after all your generator is generating images or fake images. So those images need to be, of course, of the same size as your real images, so the discriminator can be confused between these two images. So that's the GAN. In this video, let's go ahead and look at conditioning that exact same GAN by providing additional information. So here, let's go ahead and provide a label information. And again, the conditional data can be anything. In the next video, let's look at pics-to-pics, where you convert one image to a different type of image. Well, the same image, but into a different modality, for example. So for that, your conditional data is going to be an image. But in this case, the conditional data is a class label for the cifar10 dataset. So how is that class label going to be used? Well, so the conditional data and the random noise are going to be added together, concatenated, and provided as input to the generator. And the generator again generates the fake images, and the discriminator also get the conditional data as an input. And using that and the image as an input, it gets trained. And by the way, this conditional data, we are going to convert that into a form that we can actually train it by using an embedding layer. So we'll see that as part of the code, but let me walk you through the code a little bit. So this is our just regular GAN, and the whole point of why we are doing conditional GAN is so we can condition it. So we can generate, instead of generating random images, we want to generate images that belong to a specific class. That's why we are trying to condition these. And we already went through the need for conditional GAN in my, not the previous one, but the video before that. So I definitely recommend you to watch those videos in these series, so it makes sense for you, even with little bit of explanation. Okay, so this image we just saw on the title screen. So let me go ahead and skip that. And this looks very busy, but it does make sense for us to just have a quick look at it. This is the discriminator that we're going to define. And if you remember, in the previous tutorial, our discriminator was very easy and straightforward. It was just a binary classifier. Even in this case, it is a binary classifier, except here we have two inputs going into our discriminator model. One is our label, and the other one is an actual image. Previously, we only had an actual image as input. That's exactly why the model looked very simple, because we used sequential method in keras to define our model, where you just do model.add, convolution, model.add, whatever activation, and so on. You cannot do that. You need a functional, you need to use the functional API of keras to create a model that takes multiple inputs or multiple outputs, or it doesn't flow in a linear fashion. So let's go through this line by line again. This should make good sense once we go through, in a line by line fashion. So first of all, what inputs do we have to our discriminator? First, definitely an image of this size, and then a class label of that size. How many classes do we have? 10 classes. Okay, so far so good. We need to define two inputs to our model, right? So eventually our model has input image and input label, but we need to get the label into the right format. So for that, let's go ahead and start with my input label. My input label is of size 1 right there. And to that, I'm going to add an embedding layer. Please watch my tutorial on embedding. Just search this YouTube channel for embedding layers. And an embedding layer, just a quick tutorial, is it converts your vector of any size into whatever the size that you actually provide here. So it's going to convert each of your labels into a vector of size 50. For example, if your labels are 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, label 0 will be a vector of 50. Label 1 will be a vector of 50. Vector of 50 with what values? Well, it's going to fill it with random values. because we haven't specified anything here. That's exactly what we want. This is think of these as weights. Yeah, so the weights can be hey normal, hey uniform. It can be ones. It can be all zeros. Obviously, we don't want to use ones or zeros. We just use random values for the most part, right? So these vectors are all initialized using some random initialization, and then after each training, they get trained as part of your training training network. Okay, so this is our embedding layer right there. And then let's go ahead and start with a dense layer, right? I mean, embedding layer need to be converted into the same size as your image so you can concatenate both values. Think of this as you're converting your image label into one of the channels of your image. If your image is RGB image, put RGB and then label as another channel. If you want to do that, your label must be of the same dimensions as your image. In our case, 32 by 32. So we need to convert our vector of size 50 into size 32 by 32, which means we need to add a dense layer where my 50 are connected to this dense layer, and then the dense layer must have enough neurons or enough nodes to be reshaped into size 32 by 32. That's exactly why we define the number of nodes as 32 by 32. 1024. Now I'm adding a dense layer with that many nodes, 1024 nodes, and my Li as my input, which is my embedding layer output. Hopefully these things make sense. So from the dense layer, we are reshaping that into 32 by 32 by 1. So all we are doing is a little trick. Taking a vector of size 50, converting that into a size of 32 by 32 by 1 with the help of dense layer, and reshaping into that 32 by 32 by 1 size. And then we are ready to accept the second input, which is our normal image. No tricks here. Our image input is just 32 by 32 by 3. Now we need to concatenate these along this channel. 32 by 32 by 3 plus 32 by 32 by 1, which makes it 32 by 32 by 4. This is my concatenated merged image input. This bottom part is exactly same as the part from our regular GAN, which is instead of your input image, now you have the merged image, where we have merged the image with our label. So down here, convolution, convolution, flatten, exactly same as before, okay? And drop out, and finally the output is going to be 1. Why? Because again, this is a binary classifier. So that's the output, and now we compile the model. First, we define the inputs and outputs. What inputs do we have for the model? Image and label. The output is my output layer coming from here. And we're going to compile it using binary cross entropy and Adam optimizer, and we're going to track accuracy metrics. Our generator is going to be very similar. It used to take only a latent vector as input to generate fake images. Now it needs latent vector and the class information as an input. That's why, again, the first few lines are exactly same, almost exactly same as before, as my discriminator, where you add a label input of size 1, and you add an embedding layer to convert that label input of size 1 into a vector of size 50, where each of your class labels, again, are of size 50. Previously, we then changed the shape of this to 32 by 32 by 1 to make it compatible with 32 by 32 by 3, so we can concatenate these two. Now, what shape does my generator input previously? The latent vector. It had a shape of 100 or whatever that you define, which means now I need to convert this embedding layer into a size of 100, so I can concatenate, and I can concatenate these two. Okay, so let's go ahead and look at is that what I have done. Let's go through the code and then walk through these again line by line. So now we are defining number of nodes as 8 by 8. Yeah, I think I should walk back what I just mentioned, because earlier I just mentioned that, okay, we need to take this 50 and convert that into something of size 100. No, sorry, I walked that back. Let's go through this. We are actually converting that into a size of 8 by 8 because eventually what we want this generator to do is give an output of 32 by 32 by 3, right? So the output of this generator is the input to my discriminator. So this output of the generator should be of the same size as my actual images, which is 32 by 32 by 3. How do I get to 32 by 32 by 3 from a latent vector of size 100? Again, if you just look at our regular GAN, this is basically modified code of our regular GAN. We took our regular GAN of latent dimension of 100, and then we added a dense layer with how many nodes? 8 by 8 by 128, and we reshaped that. So which means I need to reshape, if I want to concatenate at this point, I need to reshape my input label into 8 by 8 by 1. How do we do that? I apologize about my earlier mistake. I jumped ahead a little bit, but we are not concatenating at that point, but then at this point. So stepping back, our input label of shape 1, because this is our class labels, and then we are using embedding to convert that into each of these into a vector of 50. And now we define a dense node of size 64, because we want to reshape our input into a size of 8 by 8. So that's what our dense layer is. And then we reshape it to 8 by 8 by 1. So finally, my input representing my latent dimensions is basically this is from this point, it's like before, okay? So my latent vector input, which is a size of 100, that's what we're going to define. And then we add a dense layer of size 128 by 128 by 8, because we are going to reshape it to this size, 8 by 8 by 128. And at this point, my label input is of size 8 by 8 by 1, and my the image input is of size 8 by 8 by 128. What happens when you combine these two? Now you have a merged concatenated input that is of size 8 by 8 by 129. 9 because you add this and that. Okay, after all that, now we are ready. This bottom part is exactly same as before, where you take the merge as your input and then you apply conv2d transpose a couple of times and then conv2d, so you go from 8 by 8 by 129 all the way to 32 by 32 by 3. That's a mouthful for me to say. I'm pretty sure that's a mouthful for you to, well, that's an earful for you to hear. But if this makes sense, then you're all set when it comes to conditional generative adversarial networks. And we are not compiling this here because we are going to train the generator as part of our GAN. So let's get to that part. So here we are actually combining both generator and the discriminators. And as I mentioned earlier, the discriminator is going to be set as non-trainable, and only the generator is going to be trained as part of this combined GAN model. So first of all, what is your input to your generator model, which is basically your latent vector or noise, if you want to call that, and the label for the generator. And then the output is basically your generator output. Why am I just getting these values? Because these are going to be your inputs to the discriminator here. And the GAN output right there is going to be the final output of this entire GAN. And the inputs to your GAN are, again, your latent vector and the labels. Again, I urge you to go through this if you're seeing for the first time, and while you're coding this, just go through this, and think about each of these line by line, because it's very important for you to understand the concept of conditional GAN, so you can understand the later part, which is, for example, pix to pix or other variations of this conditional GAN. Okay, so our generator, again, the GAN is trained on using binary cross entropy, and then we are using Adam as our optimizer. So finally, how do we train it? Just like we have done in the last video for our regular GAN, which is we define a half batch, and for each of these half batches, for every epoch and every batch, you define a half batch of real images and real labels, fake images, fake labels, and go ahead and train your discriminator on this half batch, meaning you're updating the weights of your discriminator, making the discriminator better at discriminating between these two. And then you just go ahead and train your GAN. How? Well, again, you have your input and labels as input, latent vectors and labels as input, and your Y GAN, again, always to the GAN, your labels or Y is going to be ones, because you want to fool the discriminator that the fake images are real images. Okay, that's exactly why we always have this as ones. So with this as your output and these as your input to the GAN, you're going to train on a batch. Latent vector, labels. Previously we only had latent vector and Y GAN. Now we just have the labels as an additional input. Now if you guys think this is a bit fast and things are not making much of a sense, please watch the previous video on regular GAN first. Digest that, understand that first, and then come to conditional GAN. Hopefully things make a bit more sense when you do that. Okay, and finally we're going to save this. So let's go ahead and jump into our Spider IDE and continue this. Okay, so here we are, and I am using TensorFlow. I am using TensorFlow version 2.4.1 and keras 2.4.3, just in case you wonder. And all of these libraries, I don't think I even need the first one. All of these libraries are there, even in our previous video, so nothing surprising here. And I am going to import cifar10 dataset. This GAN example, I should admit, works much better on MNIST type of data, where it's easy for you to see 0, 1, 2, 3, 4 handwritten digits. It can be a bit challenging for us to interpret the output of these GANs from cifar10 dataset, because these take a lot of time to train actually. And also you need to get a very good model for generator and discriminator to get a very realistic looking images. But let's see how our output, our generated images look like. Okay, so down here we are going to load our data and plot a few random ones, or the first 25 ones, just to make sure, okay, I can clearly see the horses and a few other things. So I'm good. Let's move on. We are going to define our discriminator. We just looked at this entire thing in our PowerPoint slide deck, so no point in dwelling on it. Although if you want, you can go ahead and print the discriminator summary, so you can just get a quick idea of exactly how it looks like. So there you go. So we have two inputs. We should have input 1, input 2. Input 1 is none. This is our label input, and this is our image input, right? 32 by 32 by 3. We are using embedding layer to convert our label input into 1 by 50 vectors. And then we use a dense layer to convert this 50 into 1024. And because it is 1024, we can actually reshape it into 32 by 32 by 1. This information, and then we took an input 2 of 32 by 32 by 3 and we concatenated these two to get 32 by 32 by 4. From here the story is the same. You just take this from 32 by 32 by 4 all the way progressively down to a single, because this is a binary classification. Okay, I'm explaining things again, but I hope you don't find this to be a repetition many times. Now I'm running the generator part. Again, I didn't go through the code because we spent a lot of time going through the code on the PowerPoint slide deck. And now let's go ahead and see. So now here I have again two inputs. One for, let me click anywhere here. I don't want the help to show up. Okay, input and input. One input is a vector of size 100. This is our latent vector, another input of size 1. And then we convert this one into, I think this is what we did, 8192, and then, no, sorry. I don't know why this doesn't print it out in a specific order as I printed it here. The best thing to do is plot it and then, and then just save it as a JPEG and look at this model. But we can just go through this, 8 by 8, 64. So basically after this one, it's this 64, and then we go to 8 by 8 by 1, right? So that's what we converted that to. And this other vector of 100, we again added a dense layer to convert that to 81 by 92, 8192, and then 8192 we reshape it to 8 by 8 by 128, and then we added these two or concatenated these two to get 8 by 8 by 129 as our input to the rest of this, which is just, once you get it to this step, again it's just going to 16 16 32 32 and finally 32 by 32 by 3. Hopefully that makes sense. Now where were we? Let's go back, and now we have to define our GAN. Again, not much tricks right there. I'll share the code so you can go through all my text and thoughts right there. And as we did in our previous video, we have to have a function that gives us a bunch of real images. And why am I again doing this step? Because I'm rescaling my input unsigned integer 8, meaning our values go from 0 to 255, right? Pixel values or values in my NumPy array, just converting them to between -1 to 1, because we use I don't know where I can see, yeah, tan H activation that converts our in values between -1 to 1. So this is the reason why I'm scaling them to between -1 to 1. So that's my loading the real samples. So whenever I call this function, it gives me my real samples. Then let's generate a batch of real samples. So this one just gives us a batch of real samples, and n underscore samples is a batch. So let's say my batch size is 16. So it gives me 16 real samples and corresponding labels. Because these are real samples, the corresponding labels are going to be 1. Don't confuse these labels. Why? With the labels of cifar 0, 1, 2, 3, 4, I mean, which is a bird or a horse or something. That's why I use the term Y right here. Y refers to the whether it is a real image or a fake image. So Y equals to 1 means it's a real image. Next, we are going to generate latent points. Latent points means the vector that goes in as an input to our generator. So this is a size of 100, for example. Okay, so this is our latent point. So let's go ahead and generate this. That's going to give us both our oh, by the way, one extra step that I need to explain. There is a line here called previously we did not have that. Previously, the generate latent points, meaning when I say previously, only GAN. It gave us just a vector, random vector. Now it's going to give us a random vector along with a random label that we are generating. So it's going to give us a random vector along with a random associated random label. Now let's generate some fake samples. We generated real samples, we generated latent points, and let's generate fake samples. How do you generate fake samples? You take in the latent points as your input to the generator, and then you generate these. That's exactly what we are doing. That's why generator is the input here. And then what does generator take as an input? Latent dimensions and your labels. So that's what we are doing. And by the way, these are fake samples, which means we are classifying them as a value of 0. That's why my Y equals to 0 here. Real samples, Y equals to 1. Fake samples, Y equals to 0. Too many labels and terminology can be a bit confusing right there. So let's go ahead and run this. And finally, we are ready to train. The training part should be very similar to the last. You have to generate your real samples and provide that as input to your discriminator. Update the weights of discriminator or train the discriminator. Generate fake samples. Train the discriminator. Now keep the discriminator constant and generate the latent points, which gives us both random latent vectors and also latent, and also the labels, right? We just talked about it. And our Y for our GAN is always 1, because even if it is real or fake, we are trying to fool the discriminator into thinking that this is real. That's why we always label these images in GAN as 1, and we just train our GAN, which is basically training our generator, because in the GAN model, our discriminator is non-trainable, only the generator is trainable. That's why we are going to go ahead and save the generator model down here. Okay, so let's go ahead and run all of these up to that point. I hope you appreciate that conditional GANs are basically our GAN, except we're adding one extra thing. That extra thing is labeled here. That extra thing is going to be a separate image in the next tutorial, where we convert one image to other and so on. Okay, now let's go ahead and run this. Our latent dimension is 100. Our vector size is 100. And we define our discriminator as D model, our generator as G model, and GAN as our GAN model. And let's go ahead and load our data set, which is load real samples that pre-processes all these 50,000 images to between -1 to 1. And we can train it. Let's train it for 2 epochs so we can see something on the screen. Let's go ahead and print this out as epoch, otherwise you would not know. This is epoch, and I think everything else is fine. Let's put a batch right there so we know what that means. Okay, sorry about that. I should not modify the code in the middle of a video, but there you go. Okay, so let's run that function. And let us run these line by line, and we are almost ready to train it. We already trained. Let's go ahead and train it. So hopefully on the screen you should see epoch 1, 2, 3, and now we are training the discriminator, putting the discriminator constant, training the generator, well, GAN, which means generator, and so on. And as you can see, epoch 1, batch number, how many out of 390, and so on. And after about so many, I lost my patience after 250 epochs. It was still getting better, but I stopped in the middle, and let's see how the output looks like. These things take a long time. You need a GPU. Okay, so how do we run this? Let's go ahead and run these lines that are going to help us down here. And first thing first, let's load the model. I saved this earlier and load the model. This took a few hours, actually. I think this took like how many hours? I think the conditional one, it took about 5 to 6 hours or so. And then I needed my system to do something else, so I had to stop it after 250 epochs. Okay, so let's generate latent points and labels. 100 by 100. Obviously, we are generating 100 points and 100 labels, right? You know what that is. And let's go ahead and get our labels ready there. And let's go ahead and predict. Model.predict. Our model is the one that we just loaded. It takes latent points and labels as input. So let's go ahead and predict. It was pretty fast. And convert our X, which is of shape 100 by 32 by 32 by 3, convert these values from float 32 to unsigned integer 8. So that's exactly what I'm trying to do, so we can plot them and things make sense. Let us hope things make sense. Okay, it's taking a while to plot. Let's see. Excuse me. I am plotting these 10 by 10 for a reason, because if you look at a single column, they all should belong to the same class. I know the images don't look like much of anything, but I hope you can understand that these all belong to the same class. These all belong to the same class, and they're all belonging to the same class. So you can see there is a trend right there. There is a trend right here. I think it wants this class to be horses or something. So you can see like some sort of a horsey structure right there. And again, I wish I trained this for another, I don't know, 500 epochs or so. I would have gotten much better looking images or output. So I didn't have that luxury, but I hope some of you guys can just leave your systems for a couple of days over the weekend to train it, and then get much more realistic looking images. If you really do happen to train that and get these, go ahead and post those in the comments part. I'm really curious about what type of images you are able to generate using this approach. Okay, in the next video, let us look at a variation of this conditional GAN, and I'm hoping to see much better results there, because pix-to-pix is a very nice way of generating realistic looking images. And for that, for a generator, we're going to use a unit. And I know for sure, as you probably know, I'm a big fan of unit. There we can expect much better realistic looking images. In fact, even here, if you go back and tweak the generator, and make it a bit more complex or something, you may actually get much better results. But again, I just wanted to show you the concept of conditional GANs, and I hope we achieved that task as part of this video. Now go ahead and jump on and then customize it for your own sake. Thank you guys, and do not forget to hit the like button and subscribe to this channel. Let's meet again in the next video.